Okay, so it's week 7, and last week I did introduce the problem set for week 6, and now I just want to go over the solution. So I'm stealing Zach's solution here, but it was fairly boilerplate. I mean, this format was given, so here's where we're going to start. You don't have the problem statement here, do you? Let me grab that. Let me grab the problem statement, week 6.
Yeah, that first question he even provides kind of a base spreadsheet that you just populate and
Yeah.
stuff, so
Yeah.
it should look pretty consistent from student to student.
Yeah. Okay, so the spreadsheet has been provided.
So I think, everything in those 2 boxes to the right starts at blank, and that's what you're asked to calculate, is like the losses.
Oh,
for
yeah.
each specific
Yeah, okay, super, thanks, okay. All right. So the first thing we're looking at is that the input to the motor, this is the electrical energy coming into the motor, is at 137 kilowatts. And so that just comes straight down from B5. The point 746 comes from the fact that there are 746 watts per horsepower. So that's your input. The motor itself is 93% efficient. So by the time we get to the belt drive, we've lost a little bit. Now we're at 170.8 horsepower. The transfer efficiency of the belt itself, and where's that going? Well, a little bit of friction, maybe a little bit of noise. So the belt itself is relatively efficient. So now you're down to 165.7 horsepower. The fan is less efficient, heat, noise, etc. So by the time we're at the end of the system, we're at 107 horsepower. So to calculate the losses, so the formula, which you can see here, if we start at B11, that's how much is going in, times 1 minus that, I'm going to try it a different way, equals, I'm just going to do a little sanity check out here, equals in minus out. I guess a little more simpler.
I think you could also do 183 divided by 0.93.
You could, yeah. So there's multiple ways to manipulate this.
Yeah.
Just in the same way that when you calculate like a Carnot efficiency, there's multiple ways to do it. So there's that. Same thing. We can just do equals. Actually, another kind of quick and slick way to do it with Excel is just do copy. So Control C, Control V. So it's just a relative function. Control V again. So we can see, yeah, that's my motor input minus the belt output. This is my from the belt to the fan, and this is finally what comes out of the fluid discharge once the fan does its thing. So at each point, we're losing some power, and let's just see how we get to this guy. Percentage, okay. All right, I'm going to try this. Give me a second. Equals product. If I multiply these 3 efficiencies by each other, it's the same.
Way to check your answer.
Yeah. I like that. That's the way I've sort of taught it. Let's put that as a percentage. 3 significant digits. There we go. So what I've just done here, I've just taken the product of the 3 efficiencies, and I came up with 58.6. In this case, it's the sum of the losses. Yeah. So each time you lose something, you're figuring out what percentage of the total it is. And yeah, it's kind of cool the way that works out.
You could just also do like 1 minus the product of the efficiencies to find the loss, right?
You could, yeah, yep. There's a lot of ways to do that. Neat,
I
okay.
tend to do those like 2 ways just to check.
Yeah.
You know,
Yeah,
it's worth doing.
cool.
The second side, you just only gave you this leftmost column and asked you to make a loss.
So this is the reverse problem.
Yeah.
Yeah,
Sorry, block.
cool, yeah. So this thing really is called the forward problem. And this is the inverse problem. And I'm just going to take one quick second to define that. I mean, this is actually a fundamental thing in engineering. So I'm just going to type this in. I have not looked at this in a while. And I'll give you one example of an inverse problem. So if you wanted to, magnetic resonance imaging or CAT scan imaging is a reverse problem, because what you're given are a big data set on 2D projections, and what you're doing is you're putting the person back together in 3D. So the forward problem is I've got an image, and like even this two-dimensional stream of me coming out is a forward problem. It's taking these pictures and shooting it back. Now, if you wanted to go and like put me back together, you'd say, okay, turn, take all of those 2D images, put it back into a 3D image. That's inverse. So I want to just take a quick peek at this. Yeah. Inverse problem in science, process of calculating a set of observations, the causal factors that produce them. And that's the one I just gave. Computer tomography is a classic one. Or calculating the density of the Earth from its gravity field, or calculating the original power coming into your power system based on what the losses are. They don't give that, I just put that in there. But it's called inverse because it starts with the results and calculates the causes. So, cool. And that's basically what we're doing here. So this is the discharge. Okay, this is what came out. We can sort of work our way back and say, well, gosh, the fan's losing some, 35%. This must be what's coming into the fan. Well, let's keep digging back to the system. Looks like the belt's losing this. This is what's coming into the belt. Oh, and the motor itself is not that efficient. Here's what's coming in the motor. So, yeah, good little sanity check. Now, this one is the urban myth, or maybe not so much, of the guy who rode out the power outage by using his Prius to power his house, because he didn't want to throw away his steaks and his milk and his eggs and whatnot in the fridge, so he knew his Prius was charged. The question is, could he actually do it? Now, what we decided is that like the fridge is sort of the critical component. I can live without TV, I can probably live without lights as long as the sun's coming up, et cetera, but I'd rather not live without food for however many days. So the fridge is what's keeping the food fresh, and it's running at, its total power is 400 watts, and it's relatively modest fridge, it's just, 100 volts times 4 amps. 4 amps is kind of small, but anyway, there it is. The fridge is not on all the time. We just estimated a duty cycle. It's on 30% of the time, which also seems a little bit high, but that's the number that came off the graph. Now we get into how much energy is required to run that refrigerator. Well, if there are 115,000 BTUs per gallon of gasoline, oh, that's right, he's going to idle the engine a little bit too. Yeah, but the car itself is going to make electricity at 110 volts, and we've done this too before when we went to Well, and a lot of cars come with a 110 built in now. Not a lot, but, you know, some do, and the Prius, in fact, does, built in. And this is just a straight-up conversion from BTUs per gallon to kilowatt hours per gallon, and then,
This number I got from the site he referenced.
Okay.
There's a graph that just simply says
Yeah.
power output of generator.
Uh-huh.
So you can answer if this is a
Valid.
reasonable way to do this or not.
Yeah.
What I essentially did was took the generator output, which is like kind of the very end output of the system.
yeah,
And divided that by the total energy content of gasoline.
okay,
So that's kind of the initial input. And if you divide 5 by 33.7, you get roughly a 15% system efficiency kind of for the entire thing. It seemed low to me, but
It does seem
those
pretty
are the
low.
numbers we're given,
it does
so-
seem pretty low.
Yeah, so,
You know, because the Carnot efficiency of the engine would probably be 40%?
see, I looked up what reasonable efficiencies are, and it was like 35.
Yeah.
It's like kind of the highest
Yeah.
end. And I used 25 here.
Yeah,
And that's the lowest end, of the Carnot efficiency.
yeah,
And so basically what I did is took the total system efficiency I get from those two, the input and output numbers, the alternate input and outputs.
Yeah.
And found efficiencies that were reasonable and kind of added up to 15%.
Yeah.
That's like a good
So
way
is-
to approach it.
is this 15, that's that 15, if I just do this, equals that divided by that,
Yeah.
about the same? Yep, 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 yep.
And so, yeah, and I that's the point of the graph on the site, is to tell you like the end use output of the generator.
Mm-hmm.
So,
That's about right, you know, it's a little like, yeah, it's a little lower than I would have expected too, but,
yeah, I think a part of it is it's really bounded by the Carnot efficiency of an engine,
Yep.
which is so low,
yep.
even though every other component's pretty high.
Mm-hmm, mm-hmm.
So, yeah, just wondering if that was like a reasonable way.
It seems pretty reasonable, and, you know, when we get to that chapter 4, I think it is, in Energy 101, you're just like, explain to me again why we heat something up to make, why are we driving thermodynamics backwards? I think heat was supposed to be the waste product, not the input, so,
Yeah.
well, yeah.
Yeah, so anyway, from that, I mean, all these other things were
Yeah.
just what you calculate.
Yeah,
The system losses part, this is where I was saying I kind of just brute force the formulas,
okay,
because, so you take the total kilowatts produced by the system,
mm-hmm,
which is E7 times C7, right? The gasoline demand times the total gasoline energy content,
mm-hmm,
minus, what did I do? All right, minus the energy content times the efficiency of the system. And so that gets you your initial loss. It's like we did in those other tables.
Yep.
You know, you drop down at each point.
yep,
I couldn't figure out one formula to just like drag and drop.
right, yeah,
And I'm confident that a formula like that exists.
yeah,
Maybe it's not even within like the capability of Excel to make happen, because it has to reference, I think you probably have to reference its own cell.
yeah, you have to avoid circular references in Excel.
But maybe there's a way to pull that off. I don't think it matters as long as the answers are right, but I sat there for a while trying to be like, is there a way that I can just make this one formula?
Well, let me dink with it a little bit. I haven't played with it a second, so give me a quick recorder going. So just to focus back where we were, we're looking at this. We're looking at this efficiency. So we've got the E7, which is how many kilowatt hours per gallon, and we're going to multiply that by E7. So E7 times C7, it's the total gasoline per week times kilowatt hours. So we're just converting to kilowatt hours. How many kilowatt hours of gasoline do we have per week, minus the kilowatt hours of gasoline per week again, times that loss, the system maintenance loss. And where'd that come from in the, what is that in Word? What's the system maintenance?
So in the article, he says that effectively by having your Prius idle in order to be a generator in the first place.
Yeah.
That alone runs at like 80%.
Oh, I see, because the car's just sitting there kind of doing nothing. There's probably some lights on, some electronics.
Some necessary systems.
Other belts are running. It's just kind of keeping itself alive.
Yeah.
Okay.
And from the way I understood it, that was separate from, the inverters, et cetera, in the car. This was just kind of like all the other accessories.
Yeah.
Which is why I just
Okay.
put it as
Well,
something.
yeah. So, yes, I mean, there's a couple different ways to write that. And so what you're looking at, this is the energy in, which is, there's your energy in, there's your gasoline in, minus the losses. So yeah, there's a lot of different ways to write that. Obviously, the change in energy and this delta energy, this is your loss. Your loss is whatever comes in versus what goes out. Or another way, I'm just going to rewrite it, En equals delta E plus E out. Another way to write it is that energy out equals the efficiency, and that's a letter eta, times E in. And so if we go up here and substitute, if this is equation 1, this is equation 2, we're basically sticking equation 1 into equation 2, and the energy out is, again, just the efficiency times delta E plus E out. So there's a lot of different ways to write this thing. There's not one exact way. And I think what you had there, Zach, was this EW, which is the energy per week, times, I'm just going to call this variable H. It's electricity per chemistry, minus, again, EW times H, eta. That's where we are with this equation 3. So I just took this guy, brought him down here, took this guy, which is the same variable, put it here, and that becomes 1 minus eta, and that is the loss. I mean, this is the equals delta E, which is what you calculated. So, yeah, I don't know if there's a slicker way or not. Brute force works. It's fine. And a lot of times, it's I mean, you can sit there in Excel and be clever and figure it out, but then if you come back, you're like, okay, how clever was I? Maybe a little too clever because I can't remember what I did. So sometimes more is actually more, I guess is the point. So, yeah. Okay. Well, I'm going to take a break with that, and then we can look at week 7.